Good afternoon. Thank you very much, Mahapatra sir, for inviting me to deliver this talk. So today I am going to present on reliability analysis of PV modules. So all of you know about that. Now PV modules are a clean source of energy, which is people are going to use on a very extensive basis. However, for the production of energy from PV modules, we need to know about what is the in our country, what may be the performance of the modules throughout its lifetime. So in this regard, this is a data from All India Survey of PV modules on reliability. Analysis for different modules throughout the country, where we have found that most of the time that degradation is more than 1%, and if we try to find about the maximum degradation, it is more than 5%. So usually, as per warranty claim of manufacturer or warranty claim of project developer, the degradation of the module should be within 1%. It will be around 0.67, 0.8%. However, we feel the degradation is a little bit high. So to know this degradation, we need to know what may be the effect, maybe the effect of environmental effect, the effect of different parameters to degrade the PV panels. First of all, why we need to understand that reliability of PV module. This is a study from series Singapore, where this is the base value of a PV module. If we install, this is Singapore dollar cents per kilowatt hour. So this is the base value, which is 12 cents per kilowatt hour. And if there is any change in the parameters of suppose or system or then your base value will be different. It means if my degradation rate is high, my base value will be you can say rupees per kilowatt hour. It will be different if my one of the parameters is going to be different. Suppose my operation is 25 years, then my base value will be different. So based on this, we can say that module is one of the major critical parameter in the PV power plant, which affect the rate of return of the PV systems. So that's why we need to know the reliability of the module, whether it will perform for 25 years in terms of performance or reliability or not. That we need to find it out. So after that, we need to know why, what may be the importance of PV power plant performance. Why we need to know about the performance of the PV power plant? Because if we are doing some investment in the field, so we need to find out what may be the financial viability of the investment. So if my modules or if my power plant is underperforming, then financial viability will be gone. So that's why we need to know what may be the degradation or what may be the baseline degradation. We need to find it out in the field, or we need to put in the module, so that our financial loss in the investment can be reduced. To reduce this rate of return, or to mitigate the risks, we need to do the proper asset management. Means what are the components we are going to install, that we need to know. And after that, we have to also find that what may be the effect, that is what may be the factors that is affecting the performance in the field, that for the short term as well as in the long term, that is also required to know. So after that, we need to find out what may be the best solution, or what may be the best component you can install in the field. Usually, there are some factors. I'm talking about as a system. There are some factors which is directly affect the system performance of the PV system. One is your maintenance issues, that is either it will be soiling or there may be some installation issues. Quality of installation may be different.
Birinchi, just a moment. Can you share your PPT again? There's some network problem.
Okay, sir.
Make it a full screen.
Is it visible?
Make it a full screen.
Is it fine?
Yeah. But make it a full screen.
Yeah, I have already. Yeah, is it fine, sir?
Yeah.
So there are some factors which is directly affect the field. So maintenance issues means, so there may be maintenance issues. One is the practices that quality of installation different, so which can damage the modules or other materials. Also, there will be some issues in the system design. So one of the major parameters which directly affect the performance of the PV system is the PV module performance. So, however, in different climate zone, that module behaves differently. So that's why we need to know about that of the module technologies as well as short-term and long-term. Also, as well as know about the BOS component, what components we are going to install and their integration rate as well. Now we come to the PV modules. The PV modules is usually characterized using a sun simulator or in the outdoor conditions at 1000 watt per meter square intensity level and module temperature and angle of light spectrum should be which we call it standard test conditions or STC. So in the simulator, we use here. This is module, and we have to take the module from the base and the module, and we need to take the of the module. If the intensity of the sunlight is below, and the noontime your intensity will have again in your in the below. So your our intensity of sunlight is changing through also angular incidence. Pulling a panel here, and angular incidence of the sunlight will be changing through it. Angular incidence is nothing but the angle between the sunlight and the normal to the module plane. That is the angular incidence, which is changing throughout the you can say 90 degree to 0 degree, then again 90 degree. So it is changing, and also that module temperature is changing in different seasons. So if I'm measuring a particular technology at a standard test conditions, which is 1000 watt per meter square, however, in the field it is different. So that's why we need to know the performance of the module. If I want to do a clear-cut modeling or clear-cut estimation, then we need to find out what may be the performance of the module in terms of real-world conditions. That's what we need to find out. I think all of you know about that. If my temperature is increasing, then my VOC will goes down and current will increase. At the same time, your power will goes down. So there are some behavior which is related to temperature and intensity also. So if the technology is different, then this behavior will be different. Means sometimes with respect to intensity, your technology may be linear. With respect to increasing intensity, your performance of the module will goes on increasing, but not in the linear way. However, at the same time, if my temperature is increasing, your performance will goes down. This is a known fact. Also, if I'm installing a panel in the field, so there may be some parameters which is directly affecting the reliability of the technology. So one of them is irradiance, which is most probably you know about UV radiation. UV radiation is the one of the major parameters which defect the module. Another one is the temperature, humidity, moisture, and it may be mechanical stress and also soiling. So these are the some factors which is directly affect the performance of the reliability of the module in the field. That performance is affected by only irradiance, temperature, and spectrum and angle of incidence, but the performance or the reliability is affected by these parameters only. This is the you can say these are the complex set of environmental stresses which is suppose if I'm installing a PV panel in the field, this factor will affect in the reliability for the 20 years or throughout its lifetime. So that's why that degradation of a particular module is directly depend on this type of stress factors. Now come to these failures. If I'm installing a panel, suppose if I for a particular climatic zone, then my degradation will be happening in the field for a different span of time. It has been observed that at the time of the installation, degradation rate is quite high. At the same time, the failure also high in some of the cases, which is we call it as infant mortality. Next, after that, after some time it gets stabilized. Okay, then the failure is rates of the modules are quite stabilized, and again after some time, the failure rates are increasing. So based on the operational time, that failure modes or you can say defects in the PV panel are different. So to check this whether the module will sustain for 25 years or not, suppose if I'm installing a panel in right now and whether it will continue for 25 years or not, we need to do some test, and there are some approved tests are there, which is there are some standards are there, which is IC 61215 and IC 61730. These two standards are used to check that whether the module will sustain it for 25 years or not in terms of power and safety. This IC 61215 is used for, we call it as qualification testing, which check whether the module will sustain for 25 years or not. And IC 61730 is suppose a panel is installed, it can give more to 25 years, no problem, but there may be some safety issues. So we have to also check whether the module is safe or not. That need to be checked it out. So these two are standards which is used to check the, you can say, reliability or qualification of the technology before installing in the field. Now, already I have mentioned about the infant failure, and one is your infant failure, midlife failure, and wear out failure. So with respect to your time of operation, your failure will be different. Okay, so in the initial point, we call it as LID. LID means light induced degradation. So suppose if I'm installing a panel in the field and that panel comes directly from the manufacturing side, and if I'm installing it, then initially your performance will goes down due to LID effect, and it may goes up to 5%. Okay, after that also you can get some failures in the junction box, in the string interconnect, glass breakage, loose frame may be there. So these are the infant failure you can observe in the field in the initial time. After that also you can find out some degradation in the ARC coating, means anti-reflection coatings are there in the glass, which is also degraded in the, you can say, infant, this may be the infant failure. Another defect, which is we call it as PID, potential induced degradation. We will learn about it later. And diode failure, cell interconnect breakage. This may be the midlife failure. So in the module, there's different parts. Okay, I think all of you know about that. What may be the different parts of the panel? Suppose glass is there, EVA is there, then cell is there. After that, and again EVA, then backseat. So in every, you can say. Degradation may be happening. So EVA discretion or excel isolation, this may be the another defect which you can find in the midlife failure. And at the end, you can find some corrosion and cell interconnect. These are the different, you can say, with respect to different years of operation, failure of different. I want to make to know this defect, or to know this failure which may be occur in the field before installation, we need to do some test, which is I already mentioned as IC61215. So these are, I am going to explain some test which is related to IC615 and 62804, which is related to PID. So one of them is critical switch. We need to do the reliability analysis of PV module is the damp-fit test. Usually, modules are installed in the field, and it can get stresses of temperature and humidity. So we need to do the test of damp fit at 85 degree temperature and 85% relative humidity, and it should be we used to do the test for 1000 hours. It means actually this is an accelerated testing condition test for a PV panel. If I want to check the reliability, or if I want to check the whether it will sustain the the module sustain in the field for a particular time or not, then I have to do this test. Actually, I have to put the module in the environmental chamber, and I have to make the conditions of the environmental chamber at 85 degrees centigrade and 85% humidity for 1000 hours. And after that, there will be some failures occurs in the module. So this may be the delamination. Actually, this is a backside of the panel. And these are some you can say bubbling, and this you can say delamination. And also you can say that adhesion of the backside is going down, and you can also find this type of corrosion in the module. So this so if you want to find the you can say reliability in terms of environmental stress of temperature and humidity, you need to do this test first. After that, there is one test, we call it as thermal cycling. As already mentioned, there's different materials in the module. One is your glass, one is your copper, and also sometimes aluminum may be there, silicon and EVA, and also tin may be there. So suppose the modules are, it is a sandwich structure. Glass is there, then EVA, then cell, then EVA, then you can say Tedlar. So every part of the module has different thermal expansion coefficient. Okay. In the morning time, your temperature of the environment is low. Okay. In the noon time, it goes on increasing, and again in the evening time also it may increase. However, in the night time, the temperature will goes down. So if the temperature is changing throughout the day, and it can this changes of temperature is happening for throughout its lifetime. So if the expansion of the is different, because their expansion coefficients are different. So suppose for silicon it is 3 into 10 to the minus 6 per Kelvin, and for EVA it is 180. So there is a huge difference. So if there is a changes in the temperature for a module in the field, then this expansion or contraction will be different. So based on that, there may be some cracks occurred in the module. Suppose this is a solar cell and this is a bake sheet and this is glass. If all the parts are expansion and contraction are different, then obviously there will be some cracks. So this is happening in the field. So to check that whether these materials are resisting that expansion and contraction in the field or not, that we need to do the test using thermal cycling. So for the thermal cycling, we have to do the test from minus 40 degrees centigrade and goes up to plus 85 degrees centigrade, and we have to do these cycles for 200 cycles we need to do. After that, we have to we can find it out whether this module sustain in the field or not in terms of you can say temperature. Sometimes these stresses can give failures like thermomechanical failures, which happens in the interconnects. Sometimes you can get cell breaking. Also, sometimes you will find glass breaking also. So these are the tests which you need to do for temperature, whether there is a problem in the expansion coefficient of the particular material or not, that we need to use thermal cycling test here. Next is, which is one of the major tests for reliability analysis, is if your environmental temperature is very low. Actually, one is we are increasing the temperature up to plus 85 degrees centigrade now, and we have to put the conditions for a particular time at 85 degrees centigrade. However, for humidity freeze test, we have to do we have to start from plus 85 and we need to come to the minus 40, and we need to put these conditions for 4 hours. So we have to put the panel in the environmental chamber. Okay. After that, we have to set the temperature at plus 85 degrees centigrade. And again, we have to reduce the temperature sharply to minus 40 degrees centigrade. And we have to keep the module for 4 hours at minus 40 degrees centigrade. And we need to check whether there is any cracks in the cells, whether there is any cracks in the glass. And sometimes you can also find some corrosion due to this test, and also sometimes delaminations are there. So this is the test if you are operating the module in a very low temperature conditions. And another test for reliability testing, which we used to do in the indoor conditions, are mechanical load test. Suppose if I'm installing a panel in the field, sometimes what will happen, there may be some vibration due to vibration in the module structure due to wind. Okay. So in that case, due to that vibration, that module get damaged. So usually there are two types of testing are there for a mechanical load test. One is static and one is the dynamic. So dynamic test is the new one, which is just come into picture for module cases. So for static mechanical load, suppose if there is any snow over the panel and high wind loads are there. So in that case, we have to give uniform stress over the panel around 2400 pascals over the panel. Okay. This is for static. If it is dynamic, then we have to give the pressure from the back side or front side, both from the both side, and we have to you can just the module we have to give pressure on the module and keep it back, and again give the pressure and keep it back. So in this way, we have to give the pressure of the panel for 1 hour, and that is the dynamic mechanical load test. So using this, you can find it out whether the module will sustain the wind load. Suppose usually people used to test the wind load test for 180 km/h wind speed. So sometimes if your modules are installed in a very high windy region, then you need to do the test as per that particular climatic zones of wind speed. Next is test which is used, one is the UV radiation and temperature test. Usually in the field, that I have already mentioned that UV is one of the major parameters which directly affect the reliability of the module. So for this, in indoor conditions, we have to give around UV doses of 15 kWh at high temperature around 60 degrees centigrade, and you can find defects like this. This is we call it as browning of UVA. So you can find these type of defects if the modules are not properly, not properly manufactured. So this is one of the critical tests which we need to do to find out the effect of UV radiation on the PV module before installation. Another test which is mostly applicable for Indian cases where high humidity and high temperatures are there. We call it as potential induced degradation. If I'm installing a PV panel in the field, which means suppose if I'm connecting the module in series connections, okay, I'm increasing that system voltage. I think already all of you know. In that case, we have to increase the system voltage to reduce the cost of the installation. Okay, if I'm installing the panel at a very high system voltage, which we call it as potential induced degradation. The degradation is basically if sodium ion is present in the glass which is used to manufacture module, and if it is ionized by somehow, and then if my cell's top surface of the cell is negative ion and that sodium is positive ion, then it may get recombined and it can flow current from the cell to the frame. So PID is nothing but at very high voltage, what is the current flowing from the cell to the frame through different paths. Suppose it may the current may flows through glass, current may flows through EVA layer or backsheet. So this is the leakage current is high, then my module will be degraded more. So this if this is two modules, single module which is before PID stress and after PID stress. If PID is there, then you can find this type of structure near the frame. It means that these cells are not working properly. So for doing this test, we have to give some high voltage around 1000 volt or 1500 volt and put the module in the environmental chamber, and for 85 degrees centigrade and 85% humidity level for around 96 hours. So after that, you can find it out whether the module is PID affected or PID resistant or not. So these are the some tests which is required to do the reliability of the PV module before installation in indoor conditions. Okay. However, suppose if I have already installed the module in the field. Okay. Now I need to find it out what may be the defects, what may be the reliability of the module in the field. So for that, we need to do this field analysis. So to identify the problems in the field, there are some present techniques are there. One is your IV testing, IR testing, EL testing. Okay, so people are now following. Suppose if I am doing just analyzing the performance of the module in the field and the power plant. So we need to just go that on-site data monitoring, which you can find the data from SCADA system, and just visual inspection you can do. This is the preliminary investigation to find out the fault in the PV power plant or PV module. After that, you can for the next level you can go string level data. You can find it out there what may be the performance of the individual string, and you can do the analysis. Okay. After that, you can find out which string is not working properly. And if you want to go more deeper level, then you can go for IR imaging. And if which IR imaging, you can find out what may be the defects occurred in the module, that you can find it out. And if you want to go more detail, then you have to do the EL testing. Now we'll go. This is the commonly used, and this is the state of art, and this is the advanced on-site technique. We'll go on later. So if I want to find it out that what may be the defect in the module, so the basic tool is we have to use IR camera, that is infrared camera. So for doing this diagnostics of the module in the field, there are different ways to do the field diagnostics to find out what may be the abnormal heat signatures in the present in the module. This is, you can use some drone camera, okay, or and also you can use some handheld camera also. So this is a PV power plant, and this is in operating conditions. If you want to do the heats, if you want to find out what may be the heat signatures, then you can use drone and run throughout the PV power plant, where you can find out what may be the heat signatures of individual modules. Okay, but if you want to go more details, then you have to do this handheld camera. And suppose this is a module where these are the cells. Okay, if you see this, then there are some bright spot in these cells. Actually, this is the hot spot. So if the temperature between these cells and the other cells are more than 20 degrees centigrade, then this is a safety issue. Okay, if it is a if it is you can say more than 10 degrees centigrade, then that is, you can call it as hotspot. Otherwise, the module will be fine. So doing this analysis, you have to first find it out that at what conditions you are doing the measurement. Means suppose the module is working, is it working conditions? It means it is at MPPT conditions, or it is in short circuit conditions, or it is in open circuit conditions. Based on that, your temperature of the module will be different. So if you are measuring the module at short circuit conditions, you can find more high temperature in the individual cells. So if you want to do the analysis of individual cells, then you need to normalize the data with respect to irradiance and ambient temperature. So you have to use these type of equations to find it out what may be the actual temperature of the module during your analysis. Next one is the EL testing. This is the little bit more advanced, where EL testing is, suppose if I am giving power to a module, it will give lights. In the same way we are giving power to the tube lights, it is illuminating. So in the same way, module also illuminate if we are giving some DC power to the module. But the wavelength of the light emitting by the module is in the more than it is not in the visible range. It is around 850 to 1100 nanometers. So to detect these signals, we have to use one different type of camera, which we call it as electroluminescence camera. So using this, you can find images like this type of images. Actually, EL images, you can say this is the X-ray of the module, where you can find what may be the defect, or which cell is producing current, or if there is any cracks there, if there is any PIDs there, then you can find it out. And for IR is nothing but this is the heat signatures, and for EL, this, you can say this is a X-ray of the particular panel. So right now, EL is the best tools if you want to do the reliability analysis in the field, because using these tools you can find out what will be the glass breakage, delamination, module string failure. Then all these parameters you can find it out in the field. So that's why most of the people prefer EL camera than IR camera to do the reliability analysis in the field. Next one is the if you want to check what may be the insulation resistance of the module in the field. Suppose the insulation resistance is nothing but this is a safety issue. The current flows between the cell and the frame. If that current is high, then you can get shock, electric shock in the field. So to check that, we have to use this type of device, which you can call it as Megger, where we have to apply a system voltage, and we have to check the current flowing from the cell to the frame. And this is one of the standard tests we need to do for insulation reliability testing in the field. And for the field, also we have to find it out what may be the degradation rate of the module. So to do this analysis, you have to use some IV tracer for the field. If you are using some IV tracer, and you can get IV curve like this, okay. But there is one problem is there. the rating of the module is written in the module in the nameplate is given in the at STC conditions. Okay. However, if you are doing the measurement in the field, you will not find any STC conditions because your intensity will be varying and your temperature will be different. So for that, you have to translate the data for a particular intensity and temperature conditions to the STC conditions by using this type of formula. Actually, there are some standard IC 60891 which you can use to translate the data for a particular intensity and temperature to the different intensity and temperature level. After that, you can find it out the degradation rate is with respect to your nameplate values and with respect to your current measured data. So from that, you can find it out that whether that module is good, bad, or whether you can use or not. That you can find it out. In future, actually, people are also doing. If you see this image, then people are also using this type of IV tracer. Means here in this type of IV tracer, the light source is already there, so no need to depend on that sun. So you can just put the IV tracer about a panel, about a module, and you can directly do that IV tracing of the module in the field, and no need to go for translation of the IV curve, so that you can get the accurate results with low uncertainty level to know the know the degradation of the module in the field. So these type of tools are coming. Also, there are new tools are coming here. Now people are doing electroluminescence imaging using handheld camera. Now, there are some companies which is also trying to find out solutions using drones also, because EL for doing EL using a handheld camera for a large power plant is very huge task. So if you are using EL cameras using some drone, then that will be you can say that is a advanced approach to find out the defect in the field or reliability analysis in the field. So these are the some examples. Suppose you can find these type of defects. This is the solar bond damages in the module. Okay, this is the front side and this is the back side. Okay, and also this type of broken glass cells you can find in the. This is the micro cracks. This is already this we call it as snail trails. Okay, you can find this type of defects in the module, and if you see through EL, then you can find this type of defects. This is we call it as you can say micro cracks or broken cells. Also, you can find corrosion like this in the field. So these are the defects which can directly reduce your reliability of the module in the field, and it can lower the performance. So this is this type of brownie you can find in the field, which is you can say major reliability issue. I have listed out some defects which you can observe in the module in terms of performance and safety. You can suppose for glass there may be some breakage. This is safety issue. There soiling is there. Glass discoloration is there, which may be a performance issue. So there are some in every component of the module there may be some safety issues, some performance issues. So we need to find it out what may be the effect of your environmental parameters for each component. So we need to analyze that particular component of the module in terms of safety or performance for different you can say different component wise. So you have to find it out, and these are the some of the list. Now, if you want to do the quantification of the reliability in the field, suppose if I want to know which defect is more severe for a particular climatic zones, or which defect I need to address for a particular climatic zones to reduce to increase my reliability in the field. So for that you can use this is a standard already exists in the literature, failure mode effect and criticality analysis, IC 60818. So here you can use one quantifying index, we call it as risk priority number, which is RPN. This is the SOD, where S is the severity, means whether suppose there is a defect in the module, whether what may be the effect of the defect in the module in terms of performance and safety. Okay. Next is occurrence. Occurrence is nothing but suppose if you're analyzing a particular PV power plant, so you can get a particular defect occurred in different types of modules and number of modules. So from that you can estimate what may be the occurrence in terms of frequency. And detection is what is the tool you are using to detect. Suppose if you are detecting the defects using some visual inspection, then you no need to use some tools. Then your detection technique will be you can say you can give rank 1. So if you are using some equipment, then you have to give more ranks. So this is the some you can say statistical tool to quantify that reliability analysis. So for doing this, you have to use suppose you have to do some visual inspection. You have to do some illuminated and dark IV also, do some insulation resistance test, also interconnect breakage test, electroluminescence imaging. Also, you have to do that thermal characterization, means IR imaging. So the basic funda is you have to go to the PV power plant and you have to choose different you can say performance of the you have to check the what may be the performance of the module in string wise, and after that you have to go individual module testing, and you can find it out some defects, or you can find it out what may be the degradation rate of the module, and after that we have to segregate the defects in terms of safety and performance failure modes. So suppose also you have to find some you will find some defects which is not affecting the performance. We call it as benign defects. Suppose if there is any scratch in the frame, then that is a defect, but it may not directly affect the performance of the module. But in the long run, or if there is some other defects are present, then it will affect the performance. We call this type of defect as benign defect, or you can also call it as cosmetic defect. So for every type of defect, we have to first segregate out the what may be the defect and what is the effect on the performance. Means suppose if corrosion in the connector is there, so what is the performance of the module based on that corrosion? You have to find it out. So based on that, you have to give severity rank. So if my performance change in the performance due to that defect is high, then I have to give high ranking of the severity. So in the same way, we have to make some groups of the particular degradation rate, and I have to give some ranking. And at the end, we have to estimate the safety and performance RPM for different defects. And so this is the formula used for occurrence. Okay. So this is the analysis for different Indian climatic zones. Actually, this is for young modules and old modules. Young modules means those which are in the field for less than 5 years, and old modules mean more than 5 years, up to you can say 30 years. So these are some defects. Suppose for wire corrosion, solder wound failure, these are the defect. These are the severity ranking. So if for young module and old module, so based on that, you can find it out that what may be the reliability, or what is the defects that is affecting the performance in the field, that you can find it out. In our analysis, we have found that solar wound failure is one of the major failure modes, which is which we find in the different climatic zones of India, which is directly affecting the performance of the module. And for in terms of safety, wire insulation is one of the major defects you can find. So these are some defects which is directly affecting the performance of the performance and safety of the PV module in different Indian climatic zones. At the same time, based on this analysis, we can also go for designing for different accelerated testing conditions to find it out whether the module is sustained in the field for 25 years or not. That we can find it out through using some this type of analysis. In the summary, asset management is the key of for any PV power plant for ensuring financial gain from the project, and at the same time, PV power plants O&M budget is not sufficient for performance evaluation, or you can say enhancing the reliability of the module. So we need to go for reliability analysis before installation. Also, we have to go for do this analysis for outdoor characterization, so that we can get a good understanding of the particular subject. Also, we have to improve the testing criteria in the outdoor conditions to get more depth analysis, so that we can design, or we can accurately quantify the performance, or we can accurately quantify that accelerated testing conditions which is required for different climatic zones. And also in future also we have to go for performance certification of the PV power plant, which could be a new business strategy for the future. Okay, this is from my side. Thank you.